Brian Schwartz is also online with me, and we're doing a live broadcast here from our offices at Vibrant Technology. This morning we're going to repeat what I had shown last week. Brian, I can still hear you through your microphone. Maybe he's going to mute it, maybe not. I'm going to go ahead and speak anyway. Hopefully you're all listening. And let me just say that these 1-hour webinars are being recorded. Another difficulty we had last month was that the recording process failed us. So when this is over, thank you for coming live today, and barring any further technical difficulties, we will record it and it will be available on our YouTube site. Vibrant has a number of video recordings on our YouTube site, so you can go there and then go through it more slowly and review what we're going to cover here today. Now, the topic of today's conversation or presentation is MEscope fault correlation tools, or something that we call FaCTs. Now, FaCTs is an acronym for fault correlation tools, and that is part of our monitoring option to MEscope. We used to call it Mechanicom. We still use that term, but we decided to go back and, for marketing reasons, use the MEscope name, and the software is really just an option to MEscope that can be purchased. So we have a number of different series of MEscope packages now. The VES, or Visual Engineering Series, is the one that we've traditionally sold for many years now. We've introduced 3 new series in addition to the VES series. One called MSS, or Machine Surveillance Series, ESS, Environmental Surveillance Series, and QTS, Quality or Qualification Testing Series. So these are all options to MEscope that use MEscope basically as a post-processing signal processor. And then I'll be showing you here this morning our console software and explain to you the database behind these other options to MEscope, where we push data into a much larger SQL database, and then we can view the data in console. And console is a separate program that is this is all network-based, so console is not licensed. You can have it on as many computers as you like. And that's where the FaCTs algorithm, the FaCTs method, has been implemented. So we're going to get there in a few minutes, and we'll look at that. But first, we're going to go into MEscope and look at how MEscope processes this data so that we can correlate different mechanical failures or faults using the FaCTs calculation. That's the whole idea. Now, at the end of this seminar, you have the ability to send us an email during the presentation, and at the end, Brian Schwartz will read your emails if you have questions, and so we will answer those questions and go back and review for any parts of the presentation that aren't clear to you. I'm going to go ahead and open up MEscope with our first project. Let me put this aside, and I'm going to make that an icon. And so here is MEscope. Let me have it fill the screen. I'm going to close this project. This is the second one we're going to look at, and I want to go back. So I'm going to close this project, and let me save it. And now I'm back on the start page in MEscope, and you can see my previous projects that I've had open on my computer. And I want to open up this one called 7 Unbalanced Cases Using FaCTs. So So I'm going to open this. I'm going to double click on this VTPRJ, and you'll see it open a number of windows in this project here in MEscope. In fact, quite a few of them. So that's quite a mess. Let me go up here to one of the hotkeys, and this one right here. If I put my mouse over these hotkeys, the first one here, it says Start Over. So that's, and we'll look at these hotkeys. I've created them all. We've had other seminars where we talk about hotkeys and macro programs. There's quite a few macro programs that are going to run in this project. They're numbered here. One is called Balanced, Small Inboard, Small Outboard, and we'll get back to these in a minute. But let me just push this Start Over button. That sounds like one that's certainly one that I want to use. Okay, so that kind of cleaned things up a little bit for me, and now I have an animated picture of a rotor kit that we have here at Vibrant, where we can simulate various things, one of them being unbalance. So this first project is going to demonstrate how we can identify different unbalanced conditions on this machine using FaCTs. Now FaCTs uses the ODS data, and we're going to take data that we've already recorded, already saved in this project from these accelerometers, the blue locations on the model. Let me go back for a minute and review some other material that's part of this project. Down here under Added Files, I've got a number of pictures, JPEGs, and a block diagram, and plus this large one here. Let me see if I can just display that. This is a PDF of a technical paper. So let's just review some of this material, and let me double click on this one, and we'll show it to you here. Okay, here's a photograph of the setup of the rotating simulator, rotating machine simulator. You can see some accelerometers. There's some on the bearing blocks here, one on each bearing block, and a couple on the base plate, and one on the motor. So those are where we took operating data and we processed it in MEscope to calculate what we call an ODS-FRF. So this is one of the functions in MEscope that you can calculate from just data that's just accelerometer data that's taken as the machine runs. And there's another picture of it. We'll come back to this picture. Here is a photo model. Now we were looking at a surface model in MEscope a minute ago in animation. We can actually turn on photographs, and here is that same model with some photographs attached to the surfaces. So we have a photo model of this particular machine in this project also. But here's the inboard rotor, the outboard rotor, and you can see this is where we put little screws into these rotors to create unbalanced conditions. Here's a block diagram of our what we used to call Mechanicom. Now we just call it machine surveillance series. So it's another series of MEscope packages that allow us to archive data into a large database. And here it is. This is a database, and I have one running on my computer with a server that's managing the data going in and out of the database. The console up here at the top can be, as I said, it's no cost. It can be installed in different computers and phones and iPads. And then down here we've got MEscope running in what we call our Vibrant Portable Hardware box. So in that box is a computer with Windows and MEscope and some acquisition hardware, so we can deploy this type of a system in the field as a portable data collection or monitoring So we can do it short-term, long-term, troubleshooting. And again, we're using the MEscope technology here, the ODS technology, and also some of the modal technology in this particular application. So I will come back to some of this. Let me close this. Let me go back and open up this paper because we're going to talk about something that's relatively new, and it's something that we have created here at FaCTs as a way to implement FaCTs, or fault correlation. This is a technical paper. You can see it's a brand new paper. It's going to be presented in January at the International Modal Analysis Conference, IMAC, in Orlando. So we're giving you a kind of a sneak preview of technical material that hasn't been presented yet, except it's all been implemented in MEscope. So if you're a current MEscope user, you can run this project. You can see how this all works. Here's an ODS FRF, just a typical measurement that we took on this machine. There's another picture of it. And so this project that we're going to use today is simply post-processing this data. And we've got 7 different simulated unbalanced cases. And FaCTs is we're going to show that FaCTs can actually identify each case from the ODS data that we take from the machine. So imagine that you've got this data, these different unbalanced cases identified in your database in terms of the ODS data that's associated with each of these cases. The FaCTs algorithm will allow us online, as we take live data, to identify one of these cases. So you can have any kind of a machine fault, and to the degree that ODS data and FaCTs can numerically identify it, then you can use this as a way of detecting or diagnosing various faults in rotating equipment. So that's the whole idea. And this could be applied to many different situations where, the term artificial intelligence or AI or neural networks, a lot of different buzzwords that are out there and different algorithms that basically do the same thing. If you put the intelligence into the database, then if that data ever shows up again, you can identify a particular machine fault. Now, let's get into a little bit of mathematics. You should be familiar with the modal assurance criterion. It's been around for many years. It's been implemented in MEscope. It was discovered, or let's say documented, starting back in the early 1980s. It was a PhD thesis topic, but we've been using it ever since. And it's basically a correlation coefficient. It's a way to tell whether two mode shapes or two ODSs are different or alike. Down here's a little bit of mathematics of the MAC value. I've got a shape U and a shape V, and they can have many components in these shapes, and the MAC is just a single number. Here's a little bit of mathematics where I multiply one shape by the other. This is what's called a dot product or a scalar product or an inner product. All those terms mean the same thing. I essentially multiply the U shape by the V shape, and I end up with a number, and then I divide by the U shape multiplied by itself, the V shape multiplied by itself. That scales my answer so that my result is always a value between 0 and 1. If the MAC is 1, that means that U and the V are the same. If the MAC is 0, that means they're basically at right angles to each other. They're orthogonal, or they're very dissimilar. Another way to think of it is that they're collinear. If U and V lie along the same straight line, then those two shapes or two vectors are collinear, lie on the same line. One of the drawbacks, though, is that I need to have at least 2 data points. So MAC does not work if I just have, let's say, two temperatures. I can't compare one temperature to another with Mac. The answer would always be 1. I've got to have at least 2 temperatures in my U and my V vector. So we invented a new calculation called SDI, and it's built into MEscope now, and we're going to use it here in a minute because it's the underlying calculation for FaCTs. And here's a formula for SDI, and it's similar, but now it's instead of multiplying U times V, we're taking the difference between U and V. So think of these as 2 ODSs or 2 mode shapes. We're going to take the difference between the two, and SDI with a little more arithmetic here is going to also have values between 0 and 1. If the two shapes are identical, then the answer is 1, and if they're different, the answer is something less than 1, and it could be as much as 0. So here's some real simple cases. When U is equal to V, SDI is 1. When V is equal to 0 or U is equal to 0, SDI is 0. So you can see that up here. I'm taking the difference between the two. So if you look in this formula right here, if either one of them is 0, the numerator is 0, and then the answer is 0. So here's some other cases here where the SDI drops in value. Now I want to go down here and show you what this SDI formula looks like. We saw this in the earlier picture when we were looking at the pictures of the machine. This is values of SDI for different values of the V vector. So when V is equal to 100, then I plot U versus V. U is along the horizontal here. So as U increases, the value of the SDI when it equals 100, then the value is 1. And as the two vectors are different, in this case just two scalars, two numbers, the answer always goes to 0. So you can see here that as V gets closer to 0, the answer still has to go through 0 for U equals 0, but the curve is very steep. And that makes this calculation very sensitive to changes between U and V. And we're going to take advantage of that here. So let's just run some cases and look at these different numbers. So I'm going to go back here. Let's close this, and let's go back and in MEscope now. Now each of these buttons up here, I'm going to push the first button. That's the balance case. That means the machine on the left and the machine on the right are both balanced. And if I look over here, here's the ODS data for each of these, and it says baseline. Well, that's really what we call balanced. And the machine is running at 2,000 RPM. Let me just make this large, and we'll take a look at the data here. So here is the ODS data in G's off of the accelerometers. So we've got 14 acceleration signals. Here's some numbers in here. They don't mean anything, but we're going to use this data to identify the different unbalanced cases. So we're running at 2,000 RPM, what's called a baseline here. Let me put that back. So in this comparison display, we're looking at the two shapes. On the left is always going to be the balanced case. On the right is going to be one of these unbalanced cases. Over here you can see the MAC. Let me push this up here. MAC value is 1. That means the two shapes are the same. SDI value is 1. That means, again, the two shapes are the same. Let me pull this down here a little bit, see if we can see that better. Now I'm going to push another button. So here is a small inboard case, small unbalance on the inboard rotor. That's a macro program that ran in the background, and it simply pulled out the ODS for a small inboard. You can see it right here. So different data, different ODS data that was taken when the machine, still running at 2,000 RPM, had a small weight on the unbalanced weight on the inboard rotor. Now you can see Mac dropped to 82%, so that's already indicating that these two shapes are different. SDI dropped all the way down to 8%, an extreme difference in the values between the balanced case and the unbalanced case. Let's try another one. This one is, we'll be able to look over here, small outboard. So here now we put the weight on the outboard instead of on the inboard. You can see the animation is scaled so that the right animation is scaled to the left being our balanced case, and you can see the machine is actually moving more. So this animated picture is not only showing me graphically that the machine's moving around more, but the MAC and the SDI are also indicating that these shapes are different. Let me try the next one, small outboard. So that's a more extreme unbalance than on the inboard. You can see we've got more motion on the outboard rotor unbalance than on the inboard. Okay, here's a large inboard. Let's see what that looks like. Okay, so we're seeing the large is causing more motion again. Large outboard, we should see even more motion. And the two indicators are telling us that, yeah, this is quite a different unbalanced case. Now here we're just comparing each unbalanced case to the balanced case. So that really isn't going to allow us to distinguish one unbalanced case from another. And we'll look at that in a minute. Let's look at the extreme case. Now we've got both rotors have an unbalance at 0 degrees. So that's an extreme case where now both rotors have unbalance and they're causing the machine to vibrate quite a bit. And you can see that in the picture. You can see that from these two indicators. Both at 90 degrees, so we've got two unbalanced weights. Not quite as bad as the 0 degrees, but still quite a lot of motion out here on the free end of the machine. And then finally, both at 180 degrees. So that means that one rotor is kind of offsetting the unbalance of the other. But still a lot of motion there. Still a lot of motion. And SDI indicating a strong difference. MAC values all around 80%. That's certainly enough significant difference from the balance to the unbalance. However, we don't have a way, just from what we've looked at here, to distinguish one unbalanced case from a different one. All we know from this so far is that the machine is unbalanced, and it's a pretty strong indication in every case. So let me go over here and look at these SDI values. I'm going to open up a shape table here that has all 7 cases in it, actually 8 cases, the balanced along with the 7 unbalanced. And we've got it for the first order, the running speed, the second order, twice the running speed, and the third order. So we can look at all those different cases also. I've actually got hotkeys up here for the first order, second order, and third order. So these macro programs that are behind the hotkeys are simply pulling data out of the shape table that I want to open up here and show you what. So here's a shape table with all 8 cases in here, and you can see all the ODS data, lots of numbers, and all this data was taken at roughly 2,000 RPM off of a set of ODS FRF measurements that were made from the accelerometers with one reference, or one Excel as a reference. I can look at the MAC values of all these ODSs with respect to one another. Now it's saying you've got something selected here, do you want to unselect? And I'll say yes. So I'm going to compare these ODSs with themselves, 8 shapes, 14 measurements. We already saw that. So here are all the MAC values. Now the ones we were seeing in the display were right along this row right here. These are all the ones in the 80% range compared to the balanced case. So shape number 1 is the balanced or the baseline, what we call baseline here. So there's a balanced machine. We just put it online and we took some data and there it is. It's running as smoothly as we can make it. As time goes on, some unbalance occurs, bearing problems, whatever. Now we can see that the MAC values are dropping. But here's the case that I want to make, and that is that here's the MAC values between all the different unbalanced cases. And I can't really tell one from another because the values are all basically 1, close to 1. So I can't sort out one case from another by using the MAC. Now let's go look at the SDI. So display SDI, and I'll do the same thing, just select now SDI is a lot better. You can see that the cases we were looking at in the animation were way down here. However, if I wanted to compare, if I wanted to sort out one unbalanced from another, for instance, number 7 and number 5, I can't tell the difference because their SDI values are 99%. So it's basically the same shape. Remember, number 7 and number 5 were on either side of the extreme case where we had 2 weights at 0 degrees. That was case number 6, I believe. Yeah, let's go over here. We can look at it right here. See, case number 6, shape number 6 was the large unbalance at 0 degrees. Case number 5 is the large inboard. Case number 7 is the large 90 degree. In other words, 2 unbalanced weights at 90 degrees. So we can't sort those 2 out. However, there's a slide bar here. And this slide bar is going to increase the sensitivity of the STI calculation by essentially moving the V vector closer to the origin. Remember that picture I showed you where U and V, the closer that V got closer to the origin, the steeper the curve got. And that's what we're going to do here. As I slide this bar up, you can see I'll go all the way up here to the top. Now those 8 cases are easily distinguishable. I can pick one from the other because their SDI values are going to be very low when I compare one case to another. And of course the diagonal is the case itself. This one here is the worst case, 33%. This is number 7 and number 5 again. So where I couldn't pick them before, now with this increased sensitivity of the SDI calculation, I can distinguish case 7 from 4 or from 5. Let's go back and look at how we did that very quickly because it's a very simple calculation. We changed, I'm going to go back into this technical paper here for a minute and just show you what the sensitivity actually is. So here are the cases we were looking at there's the MAC value and first order, here's SDI first order. We looked at those 2 cases and then they go on and look at the second and third order to see if it's, and those are all roughly the same. However, down here we're using this curve and we're going to move the V vector closer to the origin so that this curve gets more sensitive. And the easy way to do that, a simple way, is to replace the V with the sensitivity itself and the U with the difference between the 2 vectors plus the V value. So we're now just looking at, it's kind of a microscope. We're looking at the difference between U and V added to, and then added with a little sensitivity so that we've moved the V closer to the origin here so we can get a very sensitive indicator of the difference of those 2 vectors. And here's a picture that we just looked at in MEscope when we cranked that sensitivity way up high. Okay, so that's what's going on here in MEscope. Let me close this, and now let's go over into our console and look at these different cases, because now console is going to take us out into, let's say, a monitoring environment where this data is being put into the database by MEscope running in, let's say, one of our Vibrant portable boxes, or it could be just the software running in a computer acquiring data from a third-party acquisition front end. Vibrant is a software company. We're not selling the hardware. We provide it in a portable box for portable acquisition, but if you have an in situ acquisition front end, then we can post-process that data also. I'm going to slide this over. Let's just put it over here on this side and bring up, I guess I didn't do that the way I was expecting. I'm going to bring up console now, and let's make it large. And I'm going to go back here. Console's got a lot of features in it. We're not going to look at them all right here today, but here is a picture of my database on my machine and on my computer. The console database is machine-based. So when I'm using console, I can look at the data from any number of machines that I may be monitoring or that I've put in the database for various reasons. Here's an environmental Toronto Tower. This is an environmental monitoring site where, in fact, a customer is using MEscope and the database and console to monitor ground vibration at a test site. We got some other ones here, but here's the one that I want to show you. Big rotor, that's what we call it. It's offline, so I need to go back and put it online. I'm going to bring MEscope back up here, and I'm going to connect it, database connection. I want to connect to my archival database. And this little file here is a security file that comes with the software that allows you to secure your database so no one else can get into it unless they have one of these database connection files. Okay, so now we're connected. And this is how I define a machine from MEscope in the database. So this is telling me that the machine is called Big Rotor. It is in the database. It's got a structure model. We'll look at that in a minute. It's the same as this model down here. It's got a shape table that we are going to monitor values in, and it happened to be one called unbalance. I can pick one out of my MEscope. Here's all my shape tables. I can pick one out of my project, and when I archive the data, it will go into the database. Here's my animation shape table. So that's what's driving the animation. Again, we call that an expanded ODS, or in this case, we're using interpolation in the model to expand the model so it animates using the data from the accelerometers. And then we don't have any data blocks. We can actually save time or frequency data into the database for this machine. And there's a lot of other features in there, but let's just go ahead and do that. Archive in database. So I'm going to turn on the archival process in the database, and now I've just pushed this particular case into the database. And now I can go on the other side of the database in console and look at that data. So let me put this down. MEscope is running, and now I'm going to go to console, and let me double click on Big Rotor. It says it's still offline, but in fact it's here it is animating. And those hotkeys that I was using in MEscope are actually available to me here in the console. So I can remotely control MEscope wherever it is on my network. the database can be in the cloud, it can be on a company network, or I can be operating it, the console here, wirelessly. The Vibrant portable hardware has a hotspot in it, so I can just get close to the hardware box, and with MEscope running in it, I can look at what's in the database. So here I am looking at the same thing we had in the MEscope project, and you can see I've got my 8 cases up here. I can do first, second, third order. I've got the same buttons that I had in MEscope, but now I can remotely push them from console. Here's the animating picture, and here is the FaCTs diagram. And so it's a 3D picture, and I got a problem here with my driver, but let's just go on here. And you can see that what it's identified here is the first order, number 8. That was the last one in here, the balance case. Let's just go ahead and push that balance case again and see if everything is going to work properly here. Okay, so over here, MEscope actually put a little message up telling me what it did. You can see the animation cleaned up and it's balanced, and the FaCTs down here identified the first order case number 1, which is the balanced case, and its SDI value. This is SDI, and it's comparing all these different cases that it's got stored in its database, the ODS data for the 8 different cases that were previously identified in the database. Where do I do that? Let me just show you how I did that. I'm going to go back to the home, and we have something called an event log in here. So this is where I define those cases. When the data came into the database, you can see this was done back earlier this year. It stays in your database. All these different unbalanced cases. So anytime new data comes into the database, FaCTs will run the calculation of SDI with the data it has identified as a fault condition, and it will identify the particular fault. So that's the whole idea here. Let me go back to make this large, and I'm going to go back and push a different button. So I can push, let's go to the worst case here. Let me put the picture back up. I'll put this, I want to get that out of there, and let's expand this, and I need to kind of arrange things vertically. Okay, so I got FaCTs over here now. Let me, I think if I just do that, okay, so now we're back where we were, and there's my first order, and there's my balance condition. So now I want to go to the worst case here and show you what it looks like. Okay, 0 degrees, unbalanced on both rotors, and that data, MEscope's running and pushing that data into the database, and now we can see the picture, and it's identified case number 6. And you can see that it's got a clear indication. These are all the SDI values of the other cases that it has stored in its database, and none of those correlates with this data nearly as well as the first one. Or let's say, and these are in order, so it's going to show me the top 10 fault cases, and you can see its SDI values are very low. Now, how did I define this? Well, there's something in here called define bars. I can have as many of these FaCTs bars as I like, and this one is using data out of my event storage. So I showed you those different unbalanced cases that where the ODSs were saved in the database. And then here's the sensitivity. It's up to number 10. So this is the same in the console as what we did in MEscope by increasing the sensitivity. So I can define as many of these bars as I want. I can look at second order, third order. In this case, we're just looking at first order. Let me just push one more here. Let's go out to both at 180 degrees. And FaCTs should identify that case. Okay, you can see the animation calm down here a little bit. And I've got a lot of other features in here that, here I've got gauges. So those values are the actual values of the ODS data for the motor accelerometer, or I can go here to the bearing accelerometer and actually look at the values that are being saved. And I've got warning levels and so forth. Anyway, that's what I wanted to show you from this project. Let's go to another project where we're going to use modal parameters, and we're going to use FaCTs to do something even more dramatic. Let me put this down. I'm going to go back to MEscope, and we're going to stop this project, so we'll close it. And no, I don't want to save it. And I'm going to open up this other project called JimBeam QTS. Now this is a demo of quality assurance. Now we got some new acquisition software in here, so I'm making excuses, but hopefully I'll get this all to work properly. Let's go ahead and run the macros. Now I want to take this and make sure I'm connected. I think I'm already connected to the database. Yeah, these macros in here connected MEscope to the database. Let me show you the macros. There's a whole bunch of them. These are very simple though. And what we're going to do is identify torque values. Let's go look at the test setup. Okay, so here's what we did. We took JimBeam. There's a picture of JimBeam, and an impact hammer, and a triaxial accelerometer. Now this accel can be anywhere just to measure, because we're just going to look at modal frequencies. Here's a torque wrench, and we use that torque wrench on one of these cap screws here that attaches the top plate to the back plate. Okay, there's a 4-channel analyzer, impact, very simple modal test setup, and we're just going to impact and measure FRFs and then curve fit them. So only modal frequencies are used, so the accelerometer location can be arbitrary. We're going to see the peaks in the data no matter where, as long as we're at a fairly sensitive spot. Again, the impact doesn't matter, so we're only looking at modal frequency, so I can hit the beam wherever I want to. I'm not even interested in one measurement to the next. We're going to take one measurement, one impact for each of these different cases of tightness of this cap screw. So using that torque wrench, that little screwdriver torque wrench, we set the torque to 10 inch-pounds. Now these are English units, I apologize. Inch-pounds is a very small amount of torque. Then we increased it to 15, to 20, 25, 30, 35. So 6 different cases of torque on that, and that's going to affect the modal frequencies. And we're going to curve fit the FRFs that we get from hitting it with the impact hammer and use those modal frequencies for our FaCTs bar in console. So let me again show you the data here. Now I've got all the data saved in a shape table. So here is a kind of an unusual use of a shape table, but in MEscope I can't set up FaCTs bars like we can in console, but here I simply stored the modal frequencies of 6 of the modes, just arbitrarily pick 6 of them, for each of the 6 bolt tightening cases. So that's what these frequencies are. They're just numbers. Now let's look at the correlation of these shapes here's the MAC values. They're all 1. So there's very small differences between these modal frequencies, fraction of a hertz. MAC is not a good indicator. It won't show us the differences. You can see as we go along here, each of these cases is tightening the bolt a little bit. So from the 10 inch-pounds at 155 hertz all the way to the 35 inch-pounds, it only changed by 1 hertz. But they all changed. And obviously, as we stiffen the joint, the frequencies increase. Let's go look at the SDI values. Again, I'm going to compare all the frequencies. They're all 1 also. There's the SDI values. They're not much better. But now let's crank the sensitivity up. And as I push this slide bar up, you can see the same thing is happening with these modal frequencies, because now I've moved the V vector closer to the origin, and the SDI curve is now a very sensitive indicator of these different cases. So there's my 6 cases, and I can sort them out one from another using the FaCTs calculation, or what's behind FaCTs, the SDI calculation. So let me see if I can get this all to work here. Let me just pull this over to the edge, and it's just not doing what I wanted it to do, but I'm going to make this a little smaller here, and I want to get them both up here together so you can see what's going on. Now we're already hooked up to the database. I need to go back to my machine gallery, and I need to look for the Jim beam. Here it is right here. So I'm going to open that up, and there is the screw torque. So here's FaCTs for the screw torque. Now, how did I set that up? Let's go look very quickly at how we define the bars. If I go in here, now what's going to be put into the database are the 6 frequencies for each of these cases. Let me go back here and show you how this works in MEscope first. So I've got the same hotkeys here. So I'm going to push the first button here, and you'll see that it simply acquired some data in the acquisition window. So I've got all of the cases stored here, the 6 different cases, the impact and the accelerometer response for each of the cases stored in a data block, and the acquisition window is simply pulling that data out of the data block and computing the FRF. So that's what's going on in this window here. And then I'm going to do it all under program control. So I go up here and just say acquire some data, and it's going to acquire the first 4 measurements. This is the 10 inch-pounds case. So it brought that data into the acquisition window from the data block. So this has all been pre-recorded. Now I'm going to go over, and so here are the measurements sitting here. I'm going to go over here and push the curve fit button, and you watch in this window, you'll see the curve fit occur. Bingo, that was very fast. And here are the 6 frequencies for that particular torque value. And then if I say archive, it's going to push them into the database. So now they're into the database. Let me see if I can get this all to work now from the console remotely. I'm going to put this over here, and well, let me just show you quickly, and then we're going to move on. Gauges, FaCTs, edit bar. Let's just see. Okay, so here's the bar defined for those 6 frequencies, and I just went in here and just said I want to use the 6 frequencies to define my my FaCTs, my ODS data, so that FaCTs will again look at archived data in the database and compare it with the current data that's coming in. And if I go up here, let's just push a case here, 20 inch-pounds, and see if it all works. Okay, so it acquired the data over there. Now it's come back and said, go ahead and curve fit. So I'm going to go ahead and curve fit that data. That should be occurring in MEscope. And then I'm going to archive that data. And there it is. FaCTs has identified that case, the 20 inch-pounds. There it is right there. Let's try another one. Let's try 35 inch-pounds. You can see that it dims it out for a while. We got a little bug here, so that did not occur. Let's go ahead and see if we can curve fit. And we're having a little bug with the acquisition, pulling it out of a data block, so I may not be able to see that case come up. No, it didn't. All right, well, I'm going to stop with that. I think we've seen enough of the use of the SDI calculation and the sensitivity and its use in the console with an archival database so that I can specifically identify certain mechanical faults. In this case, the torque of one of the bolts. So imagine this being used in a production environment where different parts are being assembled with mechanical assembly, bolts and nuts, and various torques. So we can set this up as a go, no-go, where we have in the database the cases, the ODS data of, in this case, frequencies of modes that have been curve fit from impact of the structure itself. All right, I'm going to wrap it up. Brian, how are we doing? Do we have any questions?
Let's see. The only question was about whether we were going to be posting this. So
we will.
Yeah.
It'll be posted, and it'll probably take a day or two. So look for that, and then you can go through the seminar again and review. We also will put these two projects. Do we provide links if they send an email so that the two projects can be, if you're an MEscope owner, you can run them in your software?
Yeah, we put a link
for this one,
on
you'll
the
need a modal
YouTube page.
Okay, there's a link on the YouTube page. You'll need a modal package in order to do this VT-PRJ. The other one, I believe, well, I don't know what the options are needed there. MEscope will tell you if you try to run the macros in that VT-PRJ and you don't have the options available to process the data. You do have all of the macro programming and hotkeys, so you can run the project without using the database itself. You need that option in order to run it, but you should be able to do this much in your MEscope without using the FaCTs and from the database in the console. All right, I think we're going to wrap it up for today, and no other questions, Brian?
No.
All right, well, thank you for listening, and I want to wish you all a Merry Christmas and a prosperous and a Happy New Year for 2016, and so our next webinar will be in January, and we'll come back together and have a different topic for you in the new year. So long for now.